Alrighty, my friends, welcome to the last installment of today's videos, or this week's videos. What I want to concentrate now that we've talked about the natural variability of climate change and how we know all of that, now I want to touch into perhaps the correlation between the two, or the correlation, I guess I should say, between temperature and CO2, and how do we know that those are linked? And then kind of where are we going from here and impacts that could be felt. I mean, I could honestly go on and on and on and on and on about impacts. I'm going to try to float through them relatively quickly, kind of just depending on how much time I can stretch out here. But know that the list that I'm going to go through is not nearly like a singular exhaustive list. There's certainly many more things that can be felt along the way. So let's get into it. So the first thing that I want to look at here is temperature versus CO2 concentration. So temperature is on the top. This is temperature variation, by the way, from about 1,000 years ago up until about 2000. And then on the bottom, we have a very averaged out version of CO2 concentrations. And I want you to take a very careful look at this. Like, pause the video or look at the slides and have a very, very careful look at where we start to see one influencing the other. So we can see, like, in terms of the average, there is overall a whole lot of variation, right? But this red line is here to kind of take out the messiness, and this is global concentrations, by the way. And we can see with temperature that the overall temperature doesn't really start to increase from the baseline until about 1900, right? And then it really doesn't start to get to above zero until about like the 1950s, right? And the concern is if you look at the CO2 concentrations, that starts to increase around like the 1850s, right? So think about what happened in the 1850s. The Industrial Revolution, right? We started to make things way more efficient for ourselves. We're tired of getting around in horse and buggy, right? As much as I would love to have gotten to school today in a horse, I'm good at the moment. It would have taken me way longer. But we can see that where there's an increase in CO2, there's not a instant reaction of temperature. And that's a big deal, right? So it's a really, really, really big take-home point that I want us to really fully understand is there's a lag in the response. We are a society of instant gratification. We want instant results. Think of all the things that are peddled to you that will give you instant results for whatever you're thinking about. And that's just not how Mother Nature works. She works that way for destroying. She doesn't work that way for creating. Okay. So, we start to see a really stark increase in CO2 concentrations and a resulting temperature increase as well. We talked about this when we talked about temperature or atmospheric composition variability and like the idea of the greenhouse effect and greenhouse gases, right? So these gases act as our blanket. So they're trapping outgoing heat. And the more you have of a material that is more efficient at trapping heat, the more heat there will be. So some folks are like, yeah, well, that's only 1,000 years worth of data. Like, we need a longer data set. Okay. Got you, fam. So here is looking at, once again, temperature on top and CO2 on the bottom of the past 800,000 years. I don't know how much longer of a data set you want. Like, what more do you want from me? Right? We've only been here for a minuscule amount of time, but we can still see an extremely clear correlation between these values, right? You could almost literally take the top graph and like superimpose it on the bottom graph and it would nearly look the same, right? It would nearly look the same. So the idea here is there's some sort of natural variation that's allowing for CO2 to be secreted and CO2 to be taken in. Maybe that's so CO2 to be like put out and CO2 to be stored. So there's something going on that's allowing for this natural back and forth process of CO2 concentration. So going back to that idea of natural climate variability, if there's more ocean, if there's more life in the ocean, we can intake more CO2, which would then cause a decrease in CO2. If there's less plant activity, less plant life, then there's more CO2 that will stay in the atmosphere, right? But we have to keep in mind that these variations are happening on geological timescales. These are not instantaneous. They look really fast, but if you zoom this out, there's so much more at play here. There's such a long time that these changes happen. And that's really the big take home point, honestly, with all of this. We think that these are small timescales, but this is 800,000 years worth of information, right? So that's the idea here. So where do we go from here? What are we starting to observe now? Well, here we go. So this is looking at the human influence of CO2 concentrations. This white dotted line is where the atmospheric CO2 has never been above in the last 800,000 years. And our current level, we can see, is right around here. The Industrial Revolution has fueled these higher CO2 concentrations in the last 2 centuries because we're taking all the CO2 that's stored in our planet as fossil fuels and we're bringing it up and we're burning it. In terms of gasoline and natural gas and coal and all that stuff, we are burning it. So we're taking it from where it's stored in the rocks in the middle of our planet, not middle, but in our planet's crust, and we're taking it out and we're burning it. Tropical deforestation is also a huge key factor in these rising levels. We're taking away the natural storer of CO2, a really big natural storer of CO2. Trees, we love them. They do great things, and we're taking them away for beef and for palm oil and for mining. Capitalism. So what I want to look at now are temperature increases. Here, we're looking at 2 maps. We're looking at temperature increases by decade for the month of March, just the month of March. On the left is March from 2000 to 2010. On the right is from 2010 to 2020. And I highly recommend that you pause this video or look at the slides more closely and really analyze what you see. What do you see? The color scale, just to explain that, I suppose, a little bit. The cooler colors indicate cooler than normal conditions, and the warm colors indicate warmer than normal conditions. What do you see? What do you see? The big thing that stands out to me is this big old red blob in the Arctic. This is huge. It's a big dark red thing. My eyes are immediately drawn to it. So this is implying that in the month of March, the Arctic is warming at a much greater rate. It is much warmer than normal compared to the rest of the world. The big thing that also sticks out to me is there's more red splotchy areas over land than over water. This goes back to the idea that water takes a lot more time and energy to heat up than land does, right? So that is very much of concern here. We can do an annual analysis of this as well. So now we're concerning the entire year, not just one particular month. Again, the left side is 2000 to 2010. The right side is 2010 to 2020. So the big thing to take home again is that in the most recent decade, there's more red. So the take home point with that is the fact that we are warming faster, or warming more, I should say, maybe not faster is the right word, but we're warming more with every decade, which is great. And by the way, these are all in comparison to the anomaly from the baseline of 1951 to 1980. You can play around with the different 30-year slots, but this is a good one because it's pretty recent. So where are we going from here? This particular slide is looking at what's called kind of like the climate model. So we're looking forward in time. And These are basically the different scenarios here. So RCP, if you look on the graph here, stands for Representative Common Pathways. And this graph is made by the Intergovernmental Panel on Climate Change, or the IPCC. Perhaps you've heard of them before. And we would realistically want to stay in this RCP 2.6 range. But I honestly don't see us doing that realistically. You'll probably notice that I take a glass empty sort of viewpoint in terms of climate change impacts and things of that nature. Not to say that there aren't people out there doing really amazing things, but just thinking about policies that are being put into place, especially one that recently just was announced. The Biden administration is going to allow for drilling in Alaska, the Willows project. So awesome, right? We're still being super dependent on fossil fuels. That's whatever. It's neither here nor there. But we realistically would want to stay in this scenario because there would be less horrifying impacts on the natural world. The warmer we get, the greater the horrifying impacts on the natural world, which is not fun. So what I want to end these next couple of minutes with is something with dealing with the IPCC still. So they come out with reports every 5 to 6 years or so. And the language that they use is very specific. So they look into things like statistical analysis, and if something is very certain, like a 95% and above, they say virtually certain. Something very likely, if I remember correctly, is about 90% chance and above, and likely I think is somewhere in like the 80s-ish% and above. And keeping in mind that this is the language that they used back in 2014, so it's been a while, right? So this is from their 5th report. Biggest ideas here are that higher maximum temperatures, meaning more hot days and heat waves over all land areas. Higher minimum temperatures, so fewer cold days and frost days and cold waves over nearly all land areas. Frequency of heavy precipitation events increasing over most areas, that is very likely. And increases in area affected by drought, that's likely. Increases in tropical cyclone activity is also likely. And since then, they've put out a new report. This was the 6th report in 2021. There were 234 authors from 63 different countries who reviewed 14,000 peer-reviewed scientific publications. So something I really want to drill in here is the fact that this is not something done by one scientist. This is an analysis, a meta-analysis, where they review stuff that's already been through this publicized peer review process. So a lot. 14,000 papers that have been performed around the world. And so they take all of that and they see what's going down. And can you imagine 234 authors? You know how hard it is to get like 3 people to do group work? Could you imagine? My goodness, the amount of emails. But the big idea here is their take-home point was that recent changes in the climate are widespread, rapid, and intensifying and unprecedented in thousands of years. Their language here has not gotten better with each report. So one thing I want to just kind of show real quick is this website showing the 6th assessment report. It's actually relatively approachable. So I encourage you to kind of play around this website. The big one here would be the Interactive Atlas. You can launch it and it can kind of like give you, you can look at regional information, which I think is really sweet. So you can kind of pick areas and figure out things that could happen in scenarios and things of that nature. So I encourage you to play around with that website if you so choose. Lots of really amazing information in there. Lots of really good work has been done to really better understand where we're going and potentially where we're going. So when we come back all together, we'll go through some of the various impacts of climate change as well as ways that we can perhaps combat climate change. So thank you for watching, and I'll see y'all on the Flippy Floppy. Bye!